All right, I'm here to walk you through Unit 5. It is one of the longer ones on here, so I'm going to go ahead and just try to fly through this as quickly as I can, filling in the blanks as we go. Undercurrent and atmospheric interaction there under Unit 5. Earth's atmosphere consists of 90 kilograms of well-mixed gases above its land and water, making up its atmosphere, which is divided into distinct layers: troposphere, stratosphere, mesosphere, thermosphere, and exosphere. I don't need to know details about each of those, just maybe the names could come up. They probably shouldn't come up on the exam. Uneven heating, there's your first blank there. Uneven heating is the sun's light energy is not evenly distributed across Earth's surface because of the angle that the sun's rays hit. It changes with the Earth's latitude, so the radiation is greatest at the equator, and then it declines as you get more and more towards the poles. Greenhouse gases are gases in the atmosphere that block heat from transmitting back to space. Most important greenhouse gases are water vapor, carbon dioxide, methane, and nitrous oxide. So as the heat comes in, tries to bounce off, the gases trap it within the atmosphere. That's usually a good thing, but not if there are too many of these gases. Over the last 400,000 years, and incorporating multiple ice ages into that equation, atmospheric CO2 has fluctuated between 180 and 300 parts per million. And you don't need to know exactly what that means. Just know that now it is around 410 parts per million. This is the highest it has been in at least 800,000 years. All right, your next blank there is the Coriolis effect. Coriolis is where Earth rotates faster at the equator than it does at the poles, because Earth is wider at the equator. So it takes the same 24 hours for everyone on Earth to rotate, but people at the equator are doing it faster. It's 24 hours still, but they're having to move faster to do it in 24 hours than people, for example, in Alaska. The circle that they're doing as the world rotates is a much smaller circle, so they can do it slower. Trade winds are permanent east to west prevailing winds that flow in the Earth's equatorial region is 0 degrees to 30 degrees on either side of the equator. You're going to have trade winds. Then your next blank there, you have your westerlies, which are prevailing winds from the west, heading in an eastward direction from the west. They're going to be in your middle latitudes between 30 and 60 degrees. And then you have your polar easterlies, which are dry, cold, prevailing winds that will be 60 and above. All right, moving on to the 5.2 surface circulation section. The first one there, blank drives the strongest ocean currents. It's wind. Drives the strongest ocean currents, which occur at the surface layer. Under the influence of the Coriolis effect, the wind-driven surface currents combine into huge gyres, is what we're looking for there. Gyres, gyres. You got your image there showing the circular motion that the gyres move in. Our next blank there, upwelling. Upwelling, which is technically one word. I'm just giving you the second part of the word there. Upwelling is the movement of large volumes of water to the surface. So it's down below, and then it comes up to the surface. Let's see. In the ocean, the densest water is on the bottom. The least dense water is on the surface. The thermohaline, this word probably will come up, so please be at least a little bit familiar with this term, is a current that is driven by temperature and density differences. So as that water is going up and down throughout the mid-levels of the ocean based on temperature and density, it's called thermohaline. All right, moving on to 5.3. The warm currents on the western side of the gyres carry a vast amount of solar heat from the equator to higher latitudes. Cold currents flow in the opposite direction, going down the eastern sides. This causes the wind directions to be dedicated by the Coriolis effect. Oscillations, be familiar with that term. They're changes in ocean circulation that affect climate in a predictable cycle. Long-term predictable cycles here, multi-year predictable cycles here. The Pacific Decadal is an example. The big example that we want you to know for the blank there is El Nino. In non-El Nino years, the trade winds push a mass of very warm surface water, pushes it away. The trade winds are pushing this warm surface water away from the coast of South America. When the trade winds slack off during an El Nino year, then that warm pool gets to just sit there off the coast of South America. So South America is your blank there. El Nino leads to high rainfall is what we're looking. High rainfall in South America. A secondary effect to that, because it creates the right conditions for mosquitoes, is an increase in disease outbreaks, especially mosquito-borne diseases. So mosquito is your missing word there. Cyclonic storms, or cyclones, are rotating storms that are generated over warm waters of the tropics that occur over a much shorter time span than an oscillation, which can be a multi-year cycle. This is a much shorter span here for your cyclones. Depending on the region where you are, your cyclones may be referred to as hurricanes, cyclones, or typhoons. For a storm to be considered a hurricane in North America, must have some sustained winds of at least 119 kilometers per hour. You probably don't know much about kilometers. So 74 miles per hour is the bottom line for it to become a hurricane. Cyclones move in counterclockwise direction in the northern hemisphere, clockwise in the southern hemisphere. This is due to the Coriolis effect. The deadliest cyclone on record is the Bula cyclone, which killed over 300,000 people in Bangladesh in 1970. The world's costliest cyclone was Hurricane Katrina. In recent decades, CO2 in the atmosphere has risen drastically. I'm going to keep on moving here as this one's going long. The main human sources of methane are fossil fuels, the digestive systems of cows and sheep. Even if you just have cows there, that's fine. The oceans have absorbed about 30% of that increased CO2 emissions. Because they're taking in all that CO2, the oceans have become more acidic. Last couple here, the warming oceans are causing sea levels to rise. This rise is due to the expansion of surface waters as they warm, and also the melting of glaciers. I bet you could have figured that one out. Global warming here, last one, is the less accurate term than global climate change. We would rather use that term. The term global climate change encompasses not just temperature, like global warming suggests, but captures the full gamut of all of the climate impacts that are taking place. So there you go. There's your Unit 5 review. Peace.